Welcome back to our ongoing deep dive into the OEIS.
Always exciting to be back.
We're diving into another fascinating integer sequence today.
Yeah.
For those of you just joining us, the OEIS, or Online Encyclopedia Integer Sequences, is
a treasure trove.
Yes, a treasure trove for number theory people like you. And today we'll be looking at A000115.
Okay, so A000115, it's all about partitions, specifically those using only the numbers 1, 2, and 5.
Okay.
In simpler terms. It tells you how many different ways you can break down any whole number into combinations of just those three numbers.
So, for instance, if we take the number 5, A000115 would tell us how many different ways we can express 5 using only 1s, 2s, and 5s?
Precisely. So you could have 5 on its own, or 2 plus 2 plus 1, or 2 plus 1 plus 1 plus 1, and so on.
Yeah.
There are actually a few more possibilities, and A000115 gives us the exact count.
That's pretty neat. But how does this connect to the broader world of number theory? What makes A000115 more than just a counting game?
Well, what's fascinating here is that A000115 is a specific case of a denumerant, denoted as DNN semicolon 125.
Okay.
Denumerants count the non-negative integer solutions to linear Diophantine equations, which, as you know, are equations where we're only looking for integer solutions.
Right. Diophantine equations are a cornerstone of number theory. So by understanding denumerants, we gain a powerful tool for tackling these types of equations.
Exactly.
That's cool.
Let's break it down further. A linear Diophantine equation takes the form a 1 times x1 plus a 2 times x2 plus ... plus ak times xk equals n, where the a values are fixed positive integers, the x values are the variables, and n is our target integer. The denumerant tells us how many different combinations of non-negative integers for those x variables will satisfy the equation.
I see. So it's like figuring out how many ways you can make change for a certain amount using only specific coin denominations.
That's a great analogy. It perfectly captures the essence of what a denumerant does.
Now, I remember seeing that A000115 has a surprisingly simple formula. A of n equals round, open parenthesis, n plus 4, close parenthesis squared, divided by 20. How does this formula manage to encapsulate the complexity of partitions with just those three numbers?
It's remarkable, isn't it? The derivation of this formula delves into the properties of quadratic residues and modulo arithmetic. But at its heart, it elegantly reflects the patterns that emerge when you start listing out the partitions for different numbers.
This formula almost seems too good to be true. Does A000115 have any other interesting formulas or properties we should be aware of?
It certainly does. There's another formula, a bit more complex, that involves a function related to the remainder when n is divided by 5. It highlights the periodic nature of this sequence and hints at its connection to modular arithmetic.
Modular arithmetic. That's a familiar concept from our number theory studies. This is all starting to connect in a fascinating way.
And the connections don't stop there. A000115 also has a distinctive recurrence relation. Each term can be calculated based on a combination of the previous terms. Following a specific pattern, it shows us that A000115 isn't just a random collection of numbers. There's a deeper, predictable structure to it.
Okay. That's really interesting. And I remember reading something about a generating function for A000115. Can you explain what that is and how it helps us understand this sequence?
A generating function is a powerful tool in mathematics. It's essentially a way to encode an entire sequence within a single expression. For A000115, the generating function is 1 divided by open parenthesis 1 minus x close parenthesis, open parenthesis 1 minus x close parenthesis, open parenthesis 1 minus x close parenthesis.
Wow.
If you were to expand this expression, the coefficient of each x term would correspond to a term in our sequence.
So it's like a compact representation of an infinite sequence. That's pretty powerful.
It is. Generating functions allow us to manipulate and analyze sequences in ways that would be much more difficult if we were just working with individual terms.
This is also fascinating. A000115 seems like a gateway to exploring all sorts of concepts in number theory, from partitions and denumerants to recurrence relations and generating functions. What else can we learn from this sequence?
Well, one intriguing aspect of A00115 is its symmetry property. It turns out that A of n equals A of open parenthesis -8 minus n, close parenthesis for all integers n. This means the sequence is mirrored around a certain point, which is a rather curious characteristic for something that's essentially counting partitions.
Whoa, that is strange. Why would a sequence about partitions have this kind of symmetry?
It's a question that begs further exploration, and it hints at the intricate web of connections within this seemingly simple sequence.
And it doesn't stop there, right? A000115 is also linked to other sequences in the OEIS. What can you tell us about those connections?
That's right. A000115 is connected to sequences like A0L8616, A001304, and A08730. These connections highlight the interconnectedness of the OEIS, revealing a hidden tapestry of mathematical relationships waiting to be discovered.
So A000115 is not just an isolated curiosity. It's a window into a richer mathematical landscape, linked to other sequences through shared properties and formulas. Could you give us a specific example of how one of these connected sequences relates to A000115?
Absolutely. Let's take A008616, for example. This sequence represents the first differences of A00000115. In simpler terms, if you take each term in A000115 and subtract the term before it, you get the corresponding term in A008616.
So it's like looking at the rate of change in A000115. Instead of focusing on the absolute number of partitions, A008616 tells us how that number is growing as we move along the sequence.
Exactly. It provides a different perspective on the same underlying structure, highlighting patterns in the growth of the partition count. This relationship between A00115 and A008616 allows us to analyze the sequence from a dynamic perspective, going beyond simply counting the partitions.
That's fascinating. Seems like each connection to another sequence unveils a layer of complexity within A000115. What other insights can we gain from exploring these relationships?
Well, let's take a look at A00000115. This sequence has a rather intriguing connection to A000115. Its first differences are also represented by A00115. It's like a two-way street between these sequences.
Hold on. So if we take the differences between consecutive terms in A00130115, we get A001304. That's pretty amazing.
It is. This reciprocity highlights the interwoven nature of these sequences. It's not a one-way relationship. They both inform and enrich our understanding of each other.
It's like A000115 is a bridge connecting A008616 and A001304 through this shared property first differences. It's a chain reaction of mathematical relationships.
We can't forget about A008000. The sequence is linked to A00000115 through pairwise sums. This means that if you take every pair of consecutive terms in A008720 and add them together, you get a term in A000115.
Wow, the way these seemingly disparate sequences are intertwined is truly mind-blowing. It makes you realize that there's so much more to discover beneath the surface of these numerical patterns.
It does. It's like piecing together a giant jigsaw puzzle. Each sequence, each formula, each connection provides another piece of the bigger picture. And as we gather more pieces, the beauty and complexity of that picture become more apparent.
This is also exciting. It feels like we've just scratched the surface of A000115.
We have. And for a number theory student like yourself, these connections must be particularly exciting to uncover.
Absolutely. Number theory is all about understanding the properties and relationships between integers. And the OEIS provides an incredible playground for exploring those relationships in ways that might not be immediately obvious.
It's like having a massive toolbox filled with all sorts of mathematical tools and gadgets. The OEIS helps us understand how to use those tools and how they're all connected to each other.
As we wrap up this part of our deep dive into A000115, what are some of the key takeaways you'd like our listeners to remember?
First and foremost, I hope you appreciate the beauty and complexity of even a seemingly simple sequence like A000115. It's a testament to the power of partitions, denumerants, and generating functions in illuminating mathematical structures.
It's a reminder that there's always more to learn, even about familiar concepts. And by exploring those concepts from different angles, we can uncover hidden depths and unexpected connections.
I also hope you're inspired to explore the OEIS further on your own. It's a treasure trove of mathematical wonders just waiting to be discovered.
It's like a vast, uncharted territory, ripe for exploration and discovery. And with each new sequence we encounter, we expand our understanding of the mathematical landscape. It really is like embarking on an exciting mathematical venture with the OEIS as our guide. But before we get carried away exploring the vast OEIS universe, let's bring it back to A000115. We talked about its connection to denumerants, but you also mentioned something about a famous mathematician who worked on this concept.
Ah, yes. You're talking about James Joseph Sylvester. He was a brilliant mathematician who made significant contributions to number theory. And he was the one who introduced this concept of denumerants. He even proved their fascinating quasi-polynomial nature.
Now, I've heard the term quasi-polynomial before, but I must admit I'm a bit fuzzy on what it actually means. Could you refresh my memory and explain it in a way that makes sense in the context of denumerants?
Of course. In essence, a quasi-polynomial behaves like a polynomial but with a twist. Its coefficients can change periodically depending on those a values in the Diophantine equation we discussed earlier. Remember, the a values are the coefficients in our linear Diophantine equation.
Okay, so the coefficients in the denumerant formula aren't necessarily fixed. They can fluctuate based on the specific Diophantine equation we're dealing with.
Exactly. And that periodicity adds another layer of complexity and intrigue to denumerants. It means that the way a denumerant behaves isn't always straightforward. There are these subtle shifts and patterns governed by those a values.
That's pretty mind-blowing. It makes you realize that even something as seemingly simple as counting solutions can lead to surprisingly deep mathematical concepts.
It certainly does. And that's what makes number theory so captivating. There's always something more to discover, some hidden structural or unexpected connection waiting to be revealed.
Speaking of hidden structures, we were discussing the generating function for A000115 earlier. You mentioned that it's a way to encapsulate the entire sequence in one neat expression. But how does that actually work in practice? How can we extract information about the sequence from this generating function?
That's a great question. The magic lies in the coefficients of the expanded generating function. Remember, the generating function for A000115 is 1 divided by open parenthesis, 1 minus x, close parenthesis, open parenthesis, 1 minus x, close parenthesis. Now, if you were to expand this expression using techniques like partial fractions or power series expansion, you would get a series of terms with increasing powers of x.
Okay, so it would look something like a polynomial with an infinite number of terms.
Precisely. And the coefficient of each x term would correspond to a term in our A000115 sequence. For example, the coefficient of the x to the fifth term would give you the fifth term in the sequence, which represents the number of ways to partition 5 using 1s, 2s, and 5s.
So by looking at the coefficients in the expanded generating function, we essentially have a roadmap to the entire A000115 sequence.
Exactly. It's a powerful tool for analyzing the sequence and even deriving formulas for specific terms.
This is starting to make more sense now. The generating function acts like a blueprint, encoding the entire sequence's structure in a compact form. It's like having a key that unlocks the hidden patterns within the sequence.
It's a great way to put it. And this concept of generating functions isn't limited to A000115. It's a powerful tool used throughout number theory and other areas of mathematics to study and manipulate sequences.
This has been a truly enlightening conversation. I feel like my understanding of A000115 has gone from a simple counting game to a deeper appreciation of its connections to various number theory concepts.
I'm glad to hear that. And remember, we've only just scratched the surface. There's still so much more to explore with A000115 and its connections to the wider mathematical landscape.
Before we wrap up this deep dive, I'd love to hear your thoughts on one final question. We've talked about how A000115 relates to partitions, denumerants, generating functions, and even other OEIS sequences. But what about its practical applications? How might understanding this sequence be useful beyond the realm of pure mathematics?
That's an excellent question, and it's one that often comes up when exploring seemingly abstract mathematical concepts. While A000115 might appear purely theoretical at first glance, its connections to denumerants and Diophantine equations hint at potential applications in various fields.
Could you give us an example of where this type of knowledge might be useful?
Certainly. Think about cryptography, for instance. Cryptography relies heavily on number theory, and Diophantine equations play a crucial role in many cryptographic algorithms. Understanding how to count solutions to these equations, which is precisely what denumerants allow us to do, can be immensely valuable in designing and analyzing secure cryptographic systems.
So, A000115 and its associated concepts could potentially contribute to making our online communications more secure. That's quite remarkable.
It is, and that's just one example. Denumerants and related concepts also have applications in areas like coding theory, resource allocation, and even theoretical physics.
This is truly inspiring. It highlights how exploring seemingly abstract mathematical ideas can lead to unexpected and valuable applications in the real world.
Exactly. It's a testament to the power and beauty of mathematics, where abstract ideas can often find concrete and meaningful expressions in our everyday lives.
It's amazing to think that something as abstract as counting partitions could have such far-reaching implications. Really underscores the interconnectedness of mathematics and the surprising ways it shows up in our lives.
Absolutely. And that's why exploring sequences like A000115 is so valuable. They offer a glimpse into deeper mathematical structures and often lead us down unexpected paths of discovery.
As we wrap up our deep dive into A000115, I want to leave our listeners with a final thought-provoking question. We've uncovered a lot about this sequence, its connection to partitions, denumerants, generating functions, and even its potential applications. But knowing all of this, how might understanding A00000115 and its related concepts help us solve other problems in number theory? What doors does this knowledge open for us?
That's a fantastic question to ponder. As we've discussed, A000115 provides a concrete example of how partitions, denumerants, and generating functions are intertwined. By mastering these concepts through the lens of A000115, we gain a deeper understanding of their power and versatility.
So it's like we've been given a set of specialized tools, and by exploring A000115, we've learned how to use those tools effectively.
Exactly. And with these tools in hand, we can tackle a wider range of number theory problems. For instance, we might encounter a new Diophantine equation. That seems daunting at first, but by applying our knowledge of denumerants, we can approach it strategically, knowing that we have methods for counting its solutions.
It's like having a key that unlocks the secrets hidden within these mathematical structures. And as we explore more sequences in the OEIS, we acquire more keys, opening up new avenues of exploration and understanding.
Precisely. The journey of mathematical exploration is never ending, and the OEIS provides a roadmap, guiding us towards new frontiers of knowledge and understanding.
So to all our listeners out there, I encourage you to dive into the OEIS, explore its vast collection of sequences, and see what wonders you can uncover. There's a whole universe of mathematical treasures waiting to be discovered. Until our next deep dive, happy exploring.